This is problem 37 from the magnetic force. 4 long parallel wires are arranged on a square of edge length 2A. So the 4 wires form a square. The edge length is 2A. The wires are separated by a distance of 2 blocks. So 1 block has a width or a height of A. We want to find the net magnetic force per unit length on each wire. The per unit length is helpful because the force is equal to IL cross B. I know the direction of the vector L, but if I don't know how long the wires are, then I don't have a value to plug in for the magnitude of the vector. But we will take care of that by dividing by L, the magnitude, bringing it over to the other side. That will give us the force per length. So, on the graphic above, we're going to sketch the direction of the magnetic force on each wire. So, if we go back to what we had in the previous example problem, we said currents in the same direction attract, currents in the opposite direction repel. So I have current going out of the page here, into the page here, out of the page here, into the page here. This one's further away, so let's ignore it for now. So these are opposite directions, these are opposite directions repel. So that would be a force this way from the wire down here, and a force this way from the wire over here. Add them together and you get something pointing this way. The net force is pointing in the same direction but a little bit smaller because for this wire here, which is carrying current in the same direction, you'd have an attractive force. It's going to be small because this is further away. So it'd still be pointing in this direction but a little bit smaller when you add that contribution. So by symmetry, we can say, since this is a square, and since if we look at this wire here, the 2 wires which are closest to that are also carrying current in the opposite direction, so that would have a force pointing away from the center of the square. This would have a force pointing away from the center of the square, and this force would be pointing away from the center of the square. Since each current has the same magnitude, and since we already figured out the direction, they're asking us to find the net magnetic force on each wire, but we're only going to do the calculation once, and then we can say by symmetry what the other ones are. Here they asked us to sketch the direction, which we did. Here they ask us how should the magnetic force on the upper left wire compare to the magnetic force on the lower right wire. Upper left, lower right, those would be pointing in the opposite direction, but they would have the same magnitude. So same magnitude, but opposite direction. Usually if they're asking us a question like this, it's a good indication that we can get out of doing a calculation if we answer the question correctly. Here they only asked us about 2 wires, but we can see that all 4 wires would have the magnitude of the force would be the same. So we're only going to do the calculation once. And if I am going to find the force using this equation here, first I have to find the field. So I get to pull out the equation that I had from the previous section for the long straight current carrying wire. Let's calculate the magnetic field on the upper left wire, and I'm going to call this wire number 1. And I have to find the magnetic field from wire number 2, from wire number 3, and from wire number 4. So the magnetic field that I need for wire number 1 is going to be the magnetic field at the location of wire number 1. The net field is going to be the magnetic field from wire 2 plus the magnetic field from wire 3 plus the magnetic field from wire 4. Okay, so the net field at this location is the field from each of the 3 wires individually, then added together. So first, magnetic field from a long straight current carrying wire is mu naught I over 2 pi r in the t hat direction. So for wire number 2, remember this is just the magnitude, so that's mu naught I divided by 2 pi. The distance between the 2 wires is 2a, and the direction is, if this is carrying current into the page, that direction would be j hat. Or you can say, if there's a circle centered on this wire here, the direction would be tangent to that circle. It would either be pointing upward or downward. By your right hand, it would be pointing upward and not downward. Okay, I'm going to hurry through the rest of this a little bit quicker. So for wire number 3, we have mu naught I divided by the distance from here to here. If we draw a triangle, and this side is 2a, and this is 2a, then the hypotenuse is 2 times the square root of 2a, and so this is 2 pi times 2 times radical 2a, and then the direction, since this is carrying current out of the page, the vector has to be tangent to the circle that's pointing like this. So that's in the negative I hat, negative j hat direction. So that's minus I hat minus j hat, but that is not a unit vector. I need t hat to be a unit vector. And so if I divide by the magnitude of minus I hat minus j hat, that would be 1 squared plus 1 squared to the 1/2. So that is divided by radical 2. So I know I went through that kind of quickly, but you should be able to check all of that on your own if you need to. Okay, and then for wire number 4, that's carrying current into the page, so the field would be pointing in the I hat direction. And that is mu naught I divided by 2 pi times 2a. Same as what we had for wire number 2, except for the unit vector. So if I add everything together, I get, well, first let's do this. This is mu naught I divided by 4 pi a. This is mu naught I divided by 4 pi a. So that's mu naught I divided by 4 pi a I hat plus j hat. So that's just these two terms with the mu naught I over 4 pi a pulled out. And then for this vector here, let's pull out the negative sign. I have a mu naught I divided by 2 times 2 is 4. Radical 2 times radical is 2, and 2 times 4 is 8, so that's an 8 pi a I hat plus j hat, since I pulled the negative sign out. And now it would be for I hat mu naught I 4 pi a minus mu naught I over 8 pi a, which leaves you with a mu naught I over 8 pi a in the positive I hat direction. And same thing for j hat. So this minus this, that would be in the positive j hat direction, and we would have the same thing outside. So that's just the magnetic field. That was review from the last section. Now we want to find the force. So now I do F, I, L crossed with B. Remember that L is the direction that the current is going in, and here the current is coming out of the page, so that is in the K hat direction. So for wire number 1, L is equal to, I'm just going to say the magnitude of that vector is L, so if it's the vector L, the magnitude is L, and it's going in the K hat direction. So now I have F, I, L crossed with B. I have my L here, I have my B there, and the force is equal to I, L, K hat crossed with mu naught I over 8 pi a I hat plus j hat. I can pull out everything, the I and the L and the mu naught I over 4 pi a, and then do the cross product. So I have mu naught I squared divided by 8 pi a, and then I have this L, which I'm going to end up dividing by to get the force per unit length. Okay, so k hat crossed with I hat, k hat crossed with I hat gives me j hat. You can check on the green sheet of useful information if you need to do that, or you can check with your right hand. So if k hat's coming out of the page and j hat's pointing up, whoops, what am I doing? K hat crossed with I hat. K hat's coming out of the page, I hat's going this way. That gives me a j hat here, and a k hat crossed with j hat. K hat's going this way, j hat's going this way. That gives me a negative I hat, and I know k hat crossed with j hat. That's not alphabetical order. That does give me a negative I hat. Then, to finish the problem, I just have to divide by L, well, to finish the magnetic force per unit length for wire 1. We're 8 pi a, and then let's put the minus I hat first and say minus I hat plus j hat. This is the minus this, which is the direction of the force, is the minus I hat plus j hat direction. So that looks good. So this is for wire 1, and then we can say by symmetry what the magnetic force per length is for the other wires. So for wire number 2, that's pointing in the positive I hat, positive j hat direction, so the magnitude is the same, but it's I hat plus j hat. For wire number 3, same magnitude, and that's in the I hat minus j hat direction, so that's I hat minus j hat. And for wire number 4, same magnitude, mu naught I squared divided by 8 pi a, that's minus I hat minus j hat. Minus I hat minus j hat. Then let's just check. This is positive, positive. This is negative, negative. This is plus I hat minus j hat. That's minus I hat plus j hat. Okay. And that concludes problem 37. So most of this was review from the magnetic field section, and then we use this equation here to find the magnetic force.